Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc in the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact. Basically, a lot of the cool stuff happening inside the universe. Of course, I don't study everything in the universe. I love being a physicist. I love being a cosmologist. I love getting to study some of these random things that happen in the universe. And I love chatting to everybody about science and about all of the cool things I get to work on. So for anyone who doesn't yet know, the idea here is that this is an interactive stream. So you people can ask me anything you want about physics, about cosmology, about academia. Ask me anything literally means you can ask me anything you want. If I don't like your question, I might not answer, but I will try to answer as best as I can. And as always, I will not have all the answers. So there might be some things there will definitely be some things I don't know the answer to. But again, interactive stream, so you will get to decide what direction this stream goes in. Based on your questions, we'll decide what we talk about. If you haven't done so yet, please do subscribe to the channel, like the video, leave a comment, press all of the buttons that make stuff happen on YouTube. It really does help. It really does help get more viewers in here, and then I get to chat to more people about the joys of being a scientist. I see we have a bunch of regulars coming in here. I see Andrew, I see Ben, I see three of the Davids. John, don't remember seeing John in a long time here. We have Scott, we have Paul. Great to see everybody. Welcome back to all of the regulars. Welcome to any first-time viewers. Great to have you all here, as always. Cool. I just launched into that introduction very quickly. No mistakes this time. The last few weeks, I keep making mistakes in the introduction. Today, I managed to get through all of it and then realized I didn't catch a breath in between. So let's catch a breath and carry on with this. So yeah, I'm a theoretical physicist based in the University of Helsinki in Finland, and I study cosmology. So that means that I study what's inside the universe, how things evolve, how things interact. Now, the universe is, of course, a very, very, very big topic. There's a lot of things one can study inside the universe. There's a lot of different things we could do in the universe. And one of the biggest things we try to do as cosmologists is try to figure out what the universe is made of and why the universe looks the way it does. Hey, Prath, great to see you as well. So we know what is inside the universe to pretty good accuracy, actually. We know that everything we can see, everything we interact with, everything from me to my T-mug to the stars you see in the night sky, all of this is normal matter. And normal matter only accounts for 5% of the energy budget of the observable universe. There's another 26.2% that is in the form of dark matter. So dark matter is this weird type of matter that interacts via the gravitational force but doesn't interact electromagnetically. This means that dark matter is basically invisible, and yet it is responsible for holding everything together. Then the remaining 69% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. Yeah. Dark energy, yes, I just read something there and mixed my words, dark energy. So how do we know these numbers? Where do these numbers come from? Well, these numbers come from the best map we have of the universe, the cosmic microwave background radiation. This here is an image of basically the earliest light in the universe, the first light in the universe. This is something that gives us a huge amount of information about cosmology. And I needed to compensate for last week where I only showed the CMB in the final minutes of the stream. So today you got it before the 5-minute mark. So what is happening here? What is this image? Well, in the early universe, there are three main components. There are protons, there are electrons, and there are photons, which are particles of light. All of these three are constantly bumping into each other. Dark matter is also there, but it's kind of just sat there doing its own thing. As the universe cools down, the protons and the electrons can come together to form the first atoms. The photons at that point get left away, they get left out, so they break away and they start traveling freely throughout the universe. These particles of light have been traveling ever since then. As they've been traveling through the universe and the universe has been expanding, these particles of light, the wavelength of these particles has been shifted towards the microwave range of the electromagnetic spectrum. And now this light is what we can see behind everything else in the cosmos. When we look at the night sky, behind the galaxies, behind the stars, behind the nebulas, behind all of that, at the background, we have this afterglow of the very early universe. Everywhere in the universe, it's cosmic and it's in the microwave range, so we call it the cosmological microwave background, the CMB for short. And by looking at the temperature differences, so what you can see here, some patches are hotter, some patches are colder, so we have the orange ones, we have the blue ones. This is related to the way the photons broke away in the early universe. So by taking these temperature differences, which are tiny temperature differences, this is 1 part in 100,000. This is a ridiculously small temperature difference. But by studying these tiny temperature differences, we get information on the statistics of what was happening in the universe 380,000 years after the end of inflation, so the time at which these particles started to break away. So by looking at this cosmic microwave background radiation, we are able to get this pie chart of what the universe is made of: 5% normal matter, 26% dark matter, 69% dark energy. We know these numbers with high level of precision thanks to the cosmic microwave background radiation. And I just wanted to launch into that. That is always a good introduction as to what I work on, the type of things you can ask me about. And because, as I said last week, I only flashed the CMB towards the end, and as you all know, the CMB does need to appear in every single one of my streams. So it did appear today as well. Today it had to appear earlier to compensate for not appearing until quite late last week. Okay, I launch into this introduction sometimes to give you all time to gather your thoughts and to think about what you're doing and what you're talking about, what you want to ask. So launch into this introduction. Now you can ask me anything you want. And yes, the differences we're talking about here are very, 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 very small. Okay, I see there are a bunch of questions, so let's go through them. And we're starting off with a slightly controversial question, or question that is not controversial, but that some people might think my answer might be controversial. So what is your opinion of Richard Feynman as a scientist? So there's always a question in academia and beyond, and in a lot of areas, of can you separate the person from their contribution to a specific field? In this case, Richard Feynman had some great contributions to science. Richard Feynman was also a misogynist who had some not so nice relationships with his students. So can you separate these two? Can you say that, Feynman was a great scientist? I'm reluctant to say that. Like, he had great contributions to the field, but also he was not a very nice person. And I think it's important to keep this in mind, because I don't believe that we should have this idea of like heroes in science, of like the lone genius who revolutionized the field, because no one is immune to being a bad person. And there's a lot of these like great scientists who we think of, who we tend to put on a pedestal, but then the effect, the negative impact they had on the people around them is substantial and is important to address. So what is my personal opinion on Feynman? I think he is overhyped, as are most scientists, because scientists by themselves do not deserve a lot of hype or idolization. So I think way too many people idolize Feynman. I think he had great contributions to the field, but he also had a negative impact on many people around him. And then there was also the question of, did his behavior perhaps in any way force out someone else from academia who perhaps could have had even bigger contributions? So I do not think we should separate the person from their contributions to the field. And while, yes, Feynman did have big contributions to the field, he was also not a great person. And I think it's important that both of these things can coexist. And it's important to bear in mind that both of these things can and are true in many cases. The same is true for Schrödinger and many other physicists who we have in mind, who might have had like a big impact on the field, and then behind the scenes or even very publicly were not great people. And being a great scientist does not give you permission to be a terrible human being. And that's something that many scientists should bear in mind and should remember. Comment from Scott: I think most successful people are complete assholes in real life, with some rare exceptions. Very much depends. I do believe there are some very good people out there, and I do believe there are some very good people in academia and beyond. But I also very much think that we have to consider people as a whole, and their contribution to the field is not enough to judge them as a person, and we should also assess their actions. This is also very true when we're considering art. Like, can you separate the art from the artist? Personally, I don't think you should, and I don't think it's easy to separate these two. Okay, so that is an answer that I know some people will absolutely agree with me, and some people will probably be upset that I've just insulted one of their heroes. And if you're in that field, I encourage you to read up on what else Feynman did. If you're offended by what I just said, I really encourage you to read up on his other actions apart from his contributions to the scientific field. Okay, Pirate, here you have a theory on black holes, hand orange covering eyes. Okay, you have a theory on black holes. That is great. I'm not sure if you're going to be able to write your whole theory out here in the text. If you can condense it into a simple question, I can answer that. But I'm not going to go through your whole theory. If you do have a theory, please feel free to write it up. and submit it to a journal and get it peer reviewed, because that is how we progress in science. We get our scientific theories peer reviewed by the community. So if you do have a theory, feel free to write it up. If you have questions about your theory and you can condense it here where I don't have to read like 50 messages, you're welcome to do so as well. But I'm not going to read a scientific paper worth of content if you post it here in the questions. But if you do have specific questions, feel free to go ahead and ask them. Okay, comment from Paul here. Is almost all of the CMB visible because space is big, or is a lot of it obscured by stuff in between? Love that question. So a lot of, when we look at the CMB, you know, I always show you this version of it. This is very much not the actual version that we see, because the satellite that took this data, which is the Planck satellite, this is a satellite that is in orbit around the sun, around the Earth as well. It's at L2, so it's at Lagrange point 2. It was. Planck is no longer operational. So Planck was at Lagrange point 2. It's still there, it's just not working, which is a kind of stable point in the orbit around the sun and the Earth. So when it takes this image of the CMB, the biggest thing it has to do is look through the galaxy. So when we actually look at this image, the like raw image, there is a big galaxy in the middle. The galaxy is in the way. In addition to the galaxy, we have other galaxies, we have other stars, we have a lot of other things in the way. So when we actually take the first image of the CMB in like different frequency bands, we get the CMB with the galaxy in the middle, big bright source, and then a few other sources that we also have to get rid of. So a lot of the CMB is actually covered by the galaxy, and then there's a lot of other patches that are covered by different galaxies. But what you can actually do is take this image at several different frequencies. So then you take it focusing on microwave frequency, then you take it at slightly different wavelengths. So each time you get different depth. And by doing that, you can more easily get rid of everything that's in the way. So the question here of like how much of, is almost all of the CMB visible? I would say that actually most of it is kind of covered by other things, mainly our galaxy and then other galaxies and other stars. But we have pretty good techniques to remove those from the image and just get the background. And mainly what we do is we take the image in multiple different frequencies and then get the one we want, or use this to kind of stack them and subtract away everything that's in our way. And actually, if you go to the like Planck images, the official image release data bank from the Planck mission, you can actually find like 10 different versions of the CMB at different frequencies. And there's different processes where they show you what the CMB looks with the galaxy, then the CMB where they've masked the galaxy, and then the CMB where they've kind of filled in what the galaxy was covering. And it's actually very cool to see the progression of how they go through these different images to end up with the one that we all know and love, which is this one here. But there are several different steps towards getting this image, and there are several different filtering processes that need to happen first. I do actually have two posters of the CMB. One is this one, and one is actually the one where you have the galaxy in the way with all of the different like 9 frequency bands. And that one is also very cool to look at because it really shows you the process that goes into getting this image and, you know, everything that we need to filter out in order to get this image. Okay, let me just check the questions quickly before we go back to this, because I see there's quite a few questions today, and that is great. It looks like the CMB could have a center. Excellent comment. I will come to that in a sec. Follow-up. So this is why I go down to the bottom, because it's often follow-ups, and then I'll go back through all of the questions. Follow-up from Paul. Do we trust all the points equally, or trust the adjusted points less than the clearly detected ones? So this is also a very good question, but in general, because when we're talking about the CMB, you know, I always show you this map. This is a very pretty map. But when we do science, we're more interested in the statistical properties. So how many red blobs are there? How many blue blobs are there? And how big these blobs are. So then if you can imagine that there's like, let's say 25% of it is masked with the galaxy, it doesn't really affect the overall thing, because we can assume that the kind of 75% that we do have is a fair representation of the rest. So we can fill it in. But then, like, do we trust this data point more than this data point? We don't really take the data points individually, because what we're doing is the statistical properties. If it was something where it mattered whether we're taking a point from the top of the image or the bottom of the image or the middle of the image, then the ones that we've had to kind of reconstruct from behind the galaxy would be less trustworthy. But because what we're doing here is like averaging over all different data points in the CMB, It doesn't really matter if the position doesn't matter. You could flip this image upside down, you could have a different center, you could have a different starting point. It doesn't matter. It would not change, it would not make a difference, because what we're really interested in is the overall statistical properties of this image, not what each individual pixel looks like. Whew, okay, comment here, you should add the second CMB poster to your slide deck too. I could add hundreds of different CMB images to my slide deck here. When I talk about the two posters I mentioned are like actual physical posters that are up in my office that I got at when I went to an open doors day at the European Space Agency headquarters in Amsterdam some years ago. One of the European Space Agency headquarters, they have like 4. And I went to one of them and I got some CMB posters for free, and those are still up in my office. And yes, we are getting lots of CMB today, and we are not done with the CMB because I saw there were more questions about the CMB already. Okay. Feel like I'm 15 minutes in and I'm already losing voice, which is not a good sign, because I'm going to be at a conference for the next 3 days. So we might have to cut the stream short today if my voice continues to go. Although I always say that and I never cut it short. So we'll see. We'll see what happens. Saying Whew, okay, sorry about that coughing fit. Let's get a drink and carry on with CMB questions. Okay, I know my tea is still too hot to drink. Tea will come soon. Comment from Scott about 10 minutes ago by now. How many times have they mapped out the CMB? It's at least 2, but is it 3? So multiple times, because the first satellite to measure it was Kobe in 1992. Sorry, in 1990, was it already 1992? In the early 1990s, Kobe measured the CMB. Then we had WMAP in the early 2000s, and then we have Planck. With Kobe, we had 2 data releases. With Planck, we had 3, so that was 3 maps of the CMB. With Planck, WMAP and Planck, we had 3 each, so that's like 8 in total. Then Boomerang was a satellite that was not a satellite, it was a telescope that was put on a hot air balloon and thrown around the Arctic air, which was very cool, and that mapped the CMB. And so we have those. I would say at least like 8 or 9 times. And then we have new satellites doing the same, or new telescopes doing the same. We have Atacama Space Telescope, Atacama Cosmology Telescope. We have the South Pole Telescope. So I would say we've mapped the CMB about 12 different times by now. And then if you count that, we do it at many different frequencies. And that in addition to the temperature one, which is the one I always show you, there's a polarization one and a lensing one. There's a substantial amount of CMB maps by now, but we all know that the absolute best one is this one, the Planck 2018 release. This is the absolute best. There are many others, but this is the best one. See lots of people saying drink some tea. Yeah, 9 times, at least 9 times, probably more. I think more than that. Yeah. Okay, back to the questions. As always, if I don't answer your question immediately, I promise I'm not ignoring you. I do try to get through all the questions. It just might take me a while to get through them all. Okay, where were we with the questions? We did how many times has the CMB been mapped? Then there was the question by Prath. Has C been constant throughout the lifetime of the universe? What could it possibly be responsible for changing it? That is a very nice question. So we talk about C being the speed of light. C is the speed of light in a vacuum. As far as we know, nothing in the universe can travel faster than light in a vacuum. And we talk about it as like being the speed of light, but it's actually kind of more the speed of information. So it is the maximum speed that things can travel in the universe in general. Has it always been constant? To the best of our knowledge, yes. So there are a lot of different tests we can do on the speed of light. And it's a very interesting question of how constant have these universal constants been? Like, has the mass of the electron changed? Has the interaction strength of things changed over the history of the universe? And the speed of light is one that we consider to be constant. So that's important to ask, is there any time dependence? To the best of our knowledge, there has been no change to the speed of light over the evolution of the universe. But this is something that we can test in different ways. We can test, what a lot of people do is test how the speed of light behaves in different environments. For an example, in a region that is super dense in the universe, or a region that is under dense where there's basically nothing, does the speed of light remain the same? And it seems like it does in every test that we've been able to do. So as to what could change the speed of light in a vacuum, I'm not sure. Of course, when the universe is filled with a plasma, for an example, then light is not traveling in a vacuum, it's traveling in the plasma. So then the speed at which the light is propagating is going to change. But the speed of light in a vacuum, to my knowledge, has not changed over the history of the universe. And I'm not really sure how it would change, because it would involve having something like tired light, where light would kind of get tired after traveling in a vacuum for a while. And this is something that is quite difficult to think of throughout the history of the universe. Now, I might be wrong about this, but nothing comes to mind that would immediately change the speed of light in a vacuum. Of course, if you can make light travel through something that is not a vacuum, then you can make it slow down. You can't make it speed up, but you can make it slow down. So nothing comes to mind that would change the speed of light in a vacuum. And so just saw the comment here by Pirate of what is CMB acronym. Yes, I've mentioned that several times, and I don't always spell it out, so apologies for that. This is the cosmic microwave background radiation. So CMB comes from cosmic microwave background. That's what the acronym stands for, and it's this light that is at the background and the microwave frequency and everywhere in the cosmos, and this is where the name cosmic microwave background radiation comes from. Some people call it CMBR and add the R for radiation, but the most commonly accepted name for this is CMB, cosmic microwave background. And that's the one we go with. Okay. Let me go back to the questions, because I try to answer ones of the related ones and then I jump around a bit, but we're going to try to answer all the questions as always. I always try to get through all of them. Doesn't always happen, but we will try. I will try my best to get through all of them. Usually I manage. Okay, how many times has the CMB map done that? Comment by Mito here. Dark matter interacts with gravitation. Does it fall in a black hole? Yes, it does. So this is a very nice question. Now, we know that a black hole is basically a region of space-time that is incredibly dense. It's a region that is so dense that nothing can escape, not even light. In order to escape the gravitational pull of a black hole, you'd have to be traveling faster than light in a vacuum. And as we just said, nothing can do that. I'm not going to go too in depth into black holes today, because I think it was last week, the entire, or like 45 minutes of the stream was about black holes. So I'm not going to go too in depth about black holes today. But because black holes just attract everything via the gravitational force, anything that interacts via the gravitational force can fall into a black hole, which means dark matter, which has mass and therefore interacts via the gravitational force, feels the pull of a black hole. So dark matter can and does fall into a black hole. This actually leads to some cool ideas of how one could potentially detect dark matter, because obviously dark matter is invisible, impossible to see directly, and therefore very difficult to actually study. However, if dark matter gets accelerated before falling into a black hole, it could actually have some type of radiation coming out of it. We know normal matter does this. As normal matter is accelerated around a black hole before being sucked in, it can produce a kind of radiation or light. And this is how you actually get kind of an accretion disk. So you get visible matter falling into a black hole, and you can see this. And this is how we often find black holes, is by seeing the matter falling into them. If dark matter did something similar, perhaps by accelerating dark matter around a black hole, you get some type of radiation, some type of effect, some type of energy. So some people actually use like highly dense regions like black holes to try to look for dark matter. Now, of course, it's very difficult, because you're using like one thing that you can't see and another thing that you can't see to try to see things. And it's quite a convoluted way, but some people are testing that idea. So dark matter does fall into a black hole, and maybe this will help us towards detecting dark matter, but we have not done so yet. Okay, back to the questions. Where were we? Okay, has C been constant throughout the lifetime of the universe? I saw there was a follow-up to that, so let me get to the follow-up of that before I jump back to the top again. Keeping with C by Brath, how is it possible that massful particles travel faster than photons in a medium and cause Cherenkov radiation? Okay, so the speed at which light moves through something is given by something that is known as like the refraction index, which is basically how much it can reflect something, how quickly light can move without interacting with other things. Now, it very much depends how you're moving through a specific medium. For an example, if you have a gas might be able to travel through a medium quite easily, whereas if you have a gas with, I'm trying to think of a good way of talking about this. So if you have a gas, this can travel through a specific medium. The thing that prevents light from traveling through a medium is being absorbed and re-emitted by atoms. So if we think when the universe was very, very dense, or it's not very dense, very opaque, like before the CMB broke, before the photons of the CMB broke away, you had this gas of photons, protons, and electrons. And what was the reason that the photons, the particles of light, weren't able to travel quickly is because they were constantly being absorbed and emitted. They were constantly bumping into everything else. Now, if you have a medium that cannot absorb the photons can travel through, and other things might be slowed down, and vice versa. If you have things that can travel unhindered, they can travel quicker than light, that might be hindered by being absorbed and re-emitted by a lot of electrons. So, follow-up question here. I mean, if photons slow down by some factor, then massive particles should also slow down by at least that factor. So it very much depends on what is causing them to slow down. In the case of photons, it's going to slow down because it's going to be absorbed and re-emitted, or it's going to interact with the electrons in some type of manner. Other particles moving through the medium might not have these same interactions, and so might be able to move freely through that medium. So while nothing can travel faster than light in a vacuum, when you're not in, because in a vacuum you don't have anything that's preventing light from moving, in other mediums you might be able to slow down light while not slowing down other things, and you might be able to slow down light but not slow down other things. Now, I finally come up with an example. I was struggling to think of an example, and the example I'm going to pick is you take a bed sheet. You take a bed sheet, you take a dark colored one. Let's not go for a white one. Please don't make this complicated. Take a dark colored bed sheet or a t-shirt, or any fabric, and hold it up to the light, and you're not going to get many photons coming through because the material is blocking the photons. However, you can get water going through. You can breathe through your sheet. Especially an example that comes to mind is if you're using an FFP2 face mask or an N95 mask, which we should still be using because pandemic ongoing, COVID's still a big thing, all of those things. If you hold up your face mask to the light, you're not going to get much light coming through, but you can still move air through this mask because of the different gaps, right? So this is how you can have, now of course, now we're thinking of a very thin fabric, but the idea is pretty much the same. You can slow down photons by making it interact with things, but that doesn't necessarily slow down everything traveling through that medium. So if in a vacuum, there is nothing to slow light down, so therefore light is always going to win the race, nothing can keep up with it. But once you have some type of medium, the light can slow down, but you're not necessarily slowing everything else down. I'm not sure if that answered the question. I feel like I went about that in a very hand-wavy, roundabout way. So if that didn't answer the question properly, please do let me know, and I'll try to find a different way of answering that. But that's a fun question, and one that I haven't actually thought about how I would answer that one. So sorry if my answer there was a bit roundabout. Okay, back up to the questions. Just a side note from Scott. It's a cool sweater. Thank you. I like this sweater. I found it in a sports shop, and it's perfect for when it's warm-ish, or sort of when it's cold but not completely cold. And now that we've warmed up and it's only like 1 or 2 degrees outside, which is up from the -10, -15 that we had last week, it's actually a good sweater to wear. And I like the colors. So thank you. And yes, it is very good to wear it in the Nordics. Okay, back up to where I was with the questions, because I'm jumping about in the questions today. So it's going to take me a while to get through all of them, especially because I'm seeing a lot of very good questions here. So we're going to try to get through all of them. Okay. A comment from Prath here. Back to the Feynman discussion. I overlooked this when I was talking about Feynman. I think only those people who he hurt have the final say on whether he's a hero or not. If they are able to say he is great in spite of his actions, then who are we to judge? Yes, I think that is an interesting perspective, that it is at the end of the day up to the people on the receiving end to decide. But also, if he's creating, or if people are creating in general a toxic environment, it's not just directly the immediate victims that are going to feel the effects, but it has a knock-on effect to the whole atmosphere and the whole environment in the scientific community. So while I do agree with you, I think it's a very nuanced conversation. Okay. I see the theory about black holes that Pirate had is that nothing actually falls into a black hole, but all matter disintegrates near the event horizon, similar to particle colliders smash particles together. Black holes disintegrate. So If that were the case, what does it disintegrate them into? Now, in the case of a particle collider, when we smash particles together, we know what they go into. This is what we're using. We're interested in what they break into. If you smash protons together, you're going to rip apart the inner parts of the proton, and you're going to see things like quarks going out. You're going to get Higgs bosons. You're going to get the different decay channels. So if stuff were ripped apart when falling into a black hole, the first question is, how would that happen? Because the gravitational force is quite weak. Now, of the four forces that govern the universe, electromagnetic force, electromagnetic force, electricity, magnetism, strong nuclear force, weak nuclear force, gravity, things fall down, weak force, radioactive decay, strong force, things hold together. Now, gravity is the weakest of the forces. In order to rip things apart, you need a huge amount of energy because you need to overcome the energy of the strong force holding things together. Gravity by itself is not strong enough to do this, which is why when something falls in a black hole, in order to rip it apart, to disintegrate, you would need a huge amount of energy that the gravitational force alone is not able to provide. So if you were to disintegrate something, you would need an additional energy source in it, apart from just the black hole. The black hole itself is just a gravitational object, and gravity is not enough to pull things apart. Otherwise, we'd also see this as things get close to the center of the Earth, for an example, where the gravitational pull is a lot stronger than it is on the surface of the Earth. We'd also see things starting to have weird effects. So it doesn't. If you want things to disintegrate when falling into a black hole, you'd need another mechanism in addition to gravity. I'm not sure if there was another follow-up message to that. I just read the three that were together. But I think, yeah, that's how I would answer that. Okay. Question from John, 20 minutes away, 20 minutes ago. I am going to catch up to the questions at some point, but first, tea. Okay, does the rate of cosmic redshift vary with the density of matter along its path to us? Like, does light redshift a different rate in cosmic voids from in galaxy clusters? Love this question, and the answer is yes, it does. Okay, so let me just scroll to the bottom, then I'll go up again, jump around again. So let me just address this one, redshift, because I love this one, and my trusted friend, the Slinky Toy, is coming out for this question. Okay, so everything in the universe, every particle has a wavelength associated to it. Every particle also has a waveform. The waveform has a wavelength, which is determined by the distance between the maximum and the minimum. As something travels throughout the universe, it gets redshifted, by which we mean this gradually gets more and more and more stretched. As it's traveling through the universe, this gets redshifted. So this leads to things getting redshifted. Now imagine, as a photon, a particle of light is traveling through the universe, there's a galaxy. Now if you imagine space-time, we always imagine space-time as this sheet, and big objects are going to distort the sheet. So imagine you have your space-time fabric, you have a big galaxy that is distorting the space-time fabric, and you have a lonely photon coming and traveling. Now, as this photon approaches the galaxy, what it's going to feel is the curvature of space-time. So this means that it's going to feel like kind of this shape, a valley. Imagine a valley. Let's just draw a picture here. This is going to be much easier if I draw a picture. I have so many things in this notebook by now on both sides of the paper. So let's just draw a galaxy here. This is a galaxy. So this is space-time. Okay, this line here is space-time. This is a galaxy. This galaxy is causing space-time to bend around it like this. So as the photon, the particle of light, our trusted little friend, gets closer to this, at some point it's going to feel the well, and it's going to travel downhill. So you have your photon, it's doing this, and suddenly it's going to travel downhill. So it's going to get blue shifted again. The photon is going to condense because it's going to kind of fall downhill. Then it gets to the other side of this potential well, and now it has to climb out of the galaxy. So it's going to get stretched again. So as it falls into the galaxy, or into the potential well around the galaxy, it's going to get blue shifted, and then when it climbs out, it's going to get red shifted again. Now, normally, this would be a net zero. Whatever redshift change is going down is the same that change is coming out. So you would not notice the galaxy. However, imagine that while it's doing this, it falls, and then by the time it climbs out again, space-time has expanded due to the expansion of the universe. This means that the amount of energy it's going to, or the amount of redshift when it climbs out of the potential well, is not going to be the same as the amount of redshift lost when climbing into the well. And this actually means there's going to be a slight difference. And this is very, very important to us, because when we're looking at, again, my favorite thing, when we're looking at the cosmic microwave background radiation, we're actually very interested. We're looking at how these photons look like, or we're looking at photons 380,000 years after the Big Bang. And these have been traveling ever since throughout the universe. So these have gone through a lot of these galactic wells. And this actually gives us a huge amount of information, because then we're going to get some regions, some photons, that are going to have an extra redshift because of going through these galaxies on their way towards us. This is very, very cool, because this is actually what allows us to map what has happened between the time the CMB was produced and today. It's by measuring the way the redshift changes when it goes in and out. Because this is what allows us to measure the expansion of the universe. If the photon falling into the galaxy, into the potential well, gained and lost the same amount of redshift, the universe would not be expanding, or this is what it would point to. But because we know there's dark energy that is causing the accelerated expansion of the universe, these photons will experience a different amount of redshift because of things like galaxies. The same is true traveling through a void, just in the other direction. And this is an effect that we can actually see in the CMB as well. We get the kind of average redshift of things, and then this additional redshift coming from the galaxies. This is something that is known technically as the Sachs-Wolf effect, and the early Sachs-Wolf effect, the late Sachs-Wolf effect, just in case anyone wants a technical name for this. And it is something that goes into the calculation of the cosmic microwave background radiation. So I think this is a very cool question that you asked, and it's a very cool like intuition here to ask that question. Where was the question? Yes, question by John Redford 25 minutes ago. Does the rate of cosmic redshift vary with the density of matter? Yes, it does. And thanks to this, we can actually measure dark energy, or study dark energy with the CMB. So I love that you asked that question, because it's a very specific question that we can answer with the CMB, and there's a lot of physics hidden behind it. So that is a very cool question to answer, in my opinion. I also like, because I talk about the cosmic microwave background radiation pretty much every week, and there are still so many aspects of it that I have not talked about in these streams. And I think this is probably the first time where I've explained the integrated Sachs-Wolf effect, or this effect of falling in and out of a potential well, when talking about the CMB in the streams, at least in the last few years. So I think it's great that you will find new ways of asking me things about the CMB that I haven't talked about before. So thank you for that question. Love that question. Okay, question from Joe Business. Looks like the CMB could have a center. It does. The CMB does have a center. And then I know there was a follow-up of the universe doesn't have a center. And this is absolutely correct. Now, the CMB, cosmic microwave background radiation, you're going to get bored of that image today. The CMB is actually centered around us. And the reason for this is because the cosmic microwave background radiation is it's basically the limit that we can have access to within our universe. The distance between us and the CMB, or this last scattering surface that we call at the time the photons scattered last off of other things, this is something that is determined by the age of the universe and the speed of light. So the CMB is always going to be a sphere centered around us. However, that does not mean that we are the center of the universe, because the CMB we are the center of our CMB, but we are not the center of the universe. Any observer in the universe will see a slightly different CMB centered around themselves, because it's basically the sphere of things you can see. Like, from where I am, if I look around in every direction, I can see probably, right now not very far because there's walls, but let's imagine I'm out in a field and I have good vision and I look around and, it's flat, there's no trees, whatever. I'm probably going to be able to see a couple 100 meters in any direction. So that's my visible sphere. And that is a sphere centered around me because I'm the one looking. That does not mean that I'm the center of the universe. I'm the center of my own universe, right? So it's the same. The CMB is just the limit of what is visible to us. So then it is centered around us. But if you travel to a star or to a planet a couple 100,000 light years away, so crossing a few galaxies over, you would see a very different CMB, and you would say that CMB is also centered around you. So everyone is the center of their own cosmic microwave background radiation, but that does not mean that the universe has a center. To people asking here if I said Sachs-Wolf, I said Sachs-Wolf. That is SACHS space Wolf, WOLFE, Sachs-Wolf. Yes, I know that it's a hard name to think about. So yes, even though the universe does not have a center, we are the center of our own cosmic microwave background, of our own sphere that forms the CMB, which is very cool. And it's also cool to think that there are aliens out there, or species out there, civilizations out there potentially, who see the CMB very, very differently. I think it's very cool that everyone has their own sphere of visibility around them. Okay, going back to the comments, there was a comment: people shouldn't idolize anyone. I agree. Yes, cosmic redshift, we covered that one. Okay, the CMB could have a center. Yes, the follow up, we did that one. Okay. Whew, so many questions today. I love the questions and such very varied topics. It's really fun. I need a tea break because tea is starting to get cold. Okay, question from James, about 30 minutes ago by now. Does the lack of an atmosphere equate to having a vacuum? If a large planet does not have an atmosphere, if possible, does this mean it has a vacuum near its surface? So the word vacuum means absolutely nothing, like very much no particles around it, absolutely nothing it could possibly interact with. Now, an atmosphere is going to be this like sphere of protection where there is a dense gas around planets. That is a gas that ideally is one that is useful to us. But you can have in betweens, right? An atmosphere requires a lot of particles, a vacuum requires absolutely none. And you can have something in between. Now, for an example, if you go to the surface of the moon, there is not much, there's no atmosphere. People say that the moon, you're kind of in like the vacuum of space, and that is true. You need, you need an astronaut suit, you need an oxygen mask, you need to be protected from the vacuum of space. So it is very much like a vacuum, but also it probably wouldn't be defined as a perfect vacuum because there might be some particles. But for basically every like in practice, it is a vacuum. So if you think that the moon has no atmosphere, it has a vacuum, the same can be true for many planets. If they don't have an atmosphere, they could have a vacuum, but there could also be something in between how the like sphere of protection and absolutely nothing. There could be like a small atmosphere or light atmosphere, and then you can go to the opposite extremes where you have Venus that has such a dense, or like Venus with such a dense atmosphere that you don't know what's happening there. So atmosphere can have many different levels. It's not either atmosphere or vacuum. It's kind of a range, but you can have planets with a vacuum around them. Okay, more questions. Back to the comment of CMB, more CMBs to my slide deck. I agree. You can have a planet without an atmosphere, absolutely. People telling me to drink tea. I am indeed drinking my tea now. I know you all told me like 20 minutes ago, but I'm drinking the tea now. Okay, see lots of comments here that I did already answer. Follow up by Joe about the universe having a center. The universe has a center. We have to be more productive. Yeah, unfortunately, the universe itself doesn't have a center. The cosmic microwave background, our sphere of visibility, does have a center. The universe itself does not have a center. As to we have to be more productive in our lives, nah. I think productivity is overrated. I think productivity is a capitalist idea. I think the humans are not designed to be productive. I think we are designed to enjoy life. Not that we're designed, but our purpose is not to maximize productivity. Our purpose should be to enjoy life. And this idea that if you're not being productive, you're not getting the most out of life. I know this is by no means what you were implying here, Joe, but I'm just in a mood these days where I'm like, I don't want to be productive. I am not put on this earth to produce. I'm put here to be happy and enjoy things. And I very much hope that productivity is not our biggest drive. Okay, I feel like I'm catching up here. There were a bunch of questions that I did answer there. Let me just go to the end again, see how things are going on here. Okay, comment by Paul here. I know I just missed one, but comment by Paul here. I think he said that we smash protons together to see the individual quarks, but I thought that quark can't exist by itself. That is very true. What you produce is a quark and anti-quark pair. So when you smash protons together, when you smash particles together at the Large Hadron Collider, what you can produce, for an example, is a couple of Higgs bosons. You can produce a top and anti-top pair. So top, anti-top are types of quarks. And it is true that quarks cannot be found individually. You'll never find one top, one bottom, one up, one down, one strange, one charm, but you can find the top and anti-top pair. You can find the bottom and anti-bottom pair. These are the heavier ones, so these are the more likely ones to find if you smash protons together. So quick answer to that, yes, we do not, it is correct that we do not see individual quarks coming out when we smash protons together, but you can get quark pairs. And depending on the energies at which you smash things together, you get what is known as different decay channels, or different channels. And these different channels have different probabilities, and it's basically like what are these protons going to smash into? What's going to come out when I smash these particles together? The most likely thing might be Higgs. This is what we were looking for at the Large Hadron Collider initially. This is what it was designed to find. But also you can produce different amount of, for an example, bottoms and tops. So you produce these, but you always produce them with a pair because you cannot have them by themselves, as you mentioned here. Okay, I feel like I'm catching up, and then I look at the comments and there are so many comments still to get through, but I love that there are so many questions today. It reminds me of the Periscope days where we get like hundreds of questions in one stream, and answering them all was always difficult. Okay, tea is gone, so I can focus on questions. Let's see, I covered all of those. I covered that one, keeping with C, Cherenkov radiation, we covered Cherenkov radiation. Where were we? Okay, question by James when I was talking about photons, traveling at different speeds through different things. There was a question by James: does light create heat energy, especially in the early universe? Does light create energy? So light by itself does not create energy, but light can carry energy. So particles of light can carry energy with them. They do carry energy. They travel really, really quickly, so they carry a lot of energy. Their energy is related to their wavelength. So when the wavelength changes, the energy changes as well. Something that has a very small wavelength, like a gamma ray, is going to be more energetic. Something that has a very long wavelength, like a radio wave, is going to be less energetic. So photons, light does carry energy. As to whether light carries heat, that is a fun thing. And I feel like light by itself doesn't necessarily carry heat. So light doesn't carry heat, but the process by which we produce light often does produce heat as well. A classic example of this is old-fashioned light bulbs, where you run electricity. It's more like the heat and the electricity. Sorry, you run electricity through some coils. These heat up, they glow, so you produce the photons, and they get warm, so you get the heat. So the photons by themselves do not really create the heat, but often you can create the photons and the heat together in specific mechanisms. And you can use photons to heat other things up, but they do not inherently carry heat themselves. They can just act on another body to create heat. So heat is always something that you get in a reaction, whereas energy is something that things can have internally. So a photon can carry energy. A photon does have energy. A photon doesn't have heat, but it can be involved in reactions that produce heat. So I hope that answers your question. That is a very fun question. Okay, light is radiation, so radiation can create heat. Yes, it can create heat. It just doesn't carry heat by itself. Okay, answered that one. When I was talking about photons being traveling through different materials, there was a follow-up question by Brass. The question your explanation raises is how photons are absorbed and re-emitted a lot more than massive particles. It's more intuitive to expect larger particles to interact more. Very good comment, but then it very much depends on how things are interacting. Now, the thing about photons is photons are the ones responsible for carrying electromagnetic force. So anytime you have any type of electric interaction or magnetic interaction, you are exchanging photons. You are exchanging these particles of light, because this is the particle that is responsible for carrying the electromagnetic force. This also means that anytime you have any type of free electron that the photon can interact with, it is going to interact with it if it has the right energy. Whereas the same is not true for other particles. For an example, neutrinos, which are more massive than photons, travel almost at the speed of light, but not quite. Neutrinos do not interact in any way via the electromagnetic force. So neutrinos can often pass through things, even if photons, particles of light, cannot. So what causes photons to be absorbed and re-emitted is basically the fact that they are carrying the electromagnetic force. So anytime you have any type of free electrons, the photons can interact with them, and this will cause them to slow down. However, other particles might be like fully bound up with electrons. If you have two atoms, where the electrons are bound up in the atoms, these two atoms might not necessarily interact in any meaningful way, but a photon will feel the electrons orbiting around these atoms and can interact with them. So photons can interact with a lot more things than many other atoms, for example. So that is how you can get more interactions with photons than other things, because photons really are carrying one of the forces with them. But I feel like this is such a cool question of like how photons move through things. And it's one that I'm just kind of improvising the explanation to here, but I'm sure if I watch this back later, I'll be like, oh, I should have explained that better. But it's a very, very fun topic. Fun fact, color is difference between the distance or mass of particles. Yes. Light radiation pattern reflect different on angles. Yeah. So when we're talking about colors, we're basically talking about different wavelengths. And this is a very nice way of looking at it, actually, because my stinky toy has colors in it. So I mentioned before that photons have energy with them, and they have their wavelength, where you have more energetic ones and less energetic ones. Less energetic ones are likely to be bluer in the visible spectrum. More energetic ones are going to be bluer. Less energetic ones are going to be redder. So the difference in color in terms of photons is basically the distance between the crests when you're looking at the wavelengths, and each color has a wavelength associated to it. When I was doing my undergrad, we all decided, as undergrads do, we all decided to learn our favorite colors by wavelength. So anytime anyone would ask us for our favorite color, we would give it in wavelength. At the time, my favorite color had a wavelength of 568 nanometers. If you want to Google that, you can figure out what color it was. Now my favorite color has very much changed, and I'm not sure what the wavelength is of my favorite color currently, but I can figure that out very easily if anyone wants to know. Okay, let's see. There's a comment by John here of awesome answer, thanks. I've been wondering about this for a while. Is this something that can be seen in the Lyman alpha forest? I'm guessing this was related to the thing of the galaxies on the redshift of how, because I answered quite a few questions, and I'm not sure when you asked that, but I think it's when I was talking about the Sachs-Wolf effect of photons falling into galaxies and climbing out. Is this something that can be seen with Lyman alpha forest? I would say no. No, because, okay, so Lyman alpha forest is what we get when we look at the hydrogen in between galaxies. As light travels through so in between galaxies, there's basically hydrogen clouds, there's dust. As light travels through this dust, it's going to be absorbed and re-emitted, absorbed and re-emitted. So if you get like a very energetic light beam coming from, for an example, the center of a galaxy, known as a quasar, you have this very high energetic light beam. It's going to travel through this gas, this hydrogen gas in between galaxies. It's going to be absorbed and re-emitted, and by the time it reaches you, you get a lot of absorption and emission lines. And by studying how this messy light looks like, having traveled through this dust, you can kind of figure out how these hydrogen clouds behave, which is really important because it lets us figure out how the underlying dark matter behaves. Now, the thing about Lyman alpha forest is it's very small scales. You know, we're talking about the average distance between galaxies. We're talking about looking on scales of megaparsec. So it's something quite like low key, where the accelerated expansion of the universe becomes less important. So when we're looking at Sachs-Wolf effect, when we're looking at Lyman alpha effects, I don't think you can see the Sachs-Wolf effect there because it's very like small. And in order to see the Sachs-Wolf effect or this like traveling through galaxies, I think you need a bigger distance. And I think the hydrogen clouds in between galaxies are too small of a place to see such a big effect. I think I might be wrong about this. I'm trying to like figure out if we've done stuff like that with Lyman alpha, but it doesn't come to mind. I'm actually going to look at that later because that seems like a very cool topic to look up on. But that is a very cool question. But my initial answer would be no, but don't quote me on that. Ooh, okay. Let's see. Where were we? I feel like I'm almost catching up. There's still some questions to answer, but I'm getting there. We're getting there. Let's see. Whew. Going back to the questions, where were we? There should be a way where I could mark what question I'm answering, because then it would be easy. Like, okay, answered until here. So we answered those. I answered those. Have to start somewhere. Not sure what that was related to, but yes, we definitely always have to start somewhere. Okay, question by Pratt 11 minutes ago. I'm catching up. I'm no longer half an hour behind. Is it possible for a planet to have more than one pair of magnetic poles? Interesting question. I've never thought about this. Intuitively, I would say no, because if you have a magnetic field around a planet, what is usually partly caused by is by the rotation of the planet as well. You have a rotating object. This is going to create some type of magnetic field. So then the poles are given by the rotation angle. Approximately, then it can be knocked off slightly. We know ours is not perfectly aligned with our rotation, but it is approximately aligned. So I'm wondering how you would get a planet with multiple magnetic poles. Interesting. I'm not sure. My intuitive answer would be no, but just because I think of two poles, like when you form a magnetic field from a spinning object, you're going to have two poles. I'm not sure if there's any way you could create multiple magnetic poles on a planet. So I'm going to say no to that. But again, this is something that I've never thought about before. So nothing's coming to mind of an example of a planet that would have multiple magnetic poles. But maybe Venus is the most productive in the atmosphere category. Yeah, Venus definitely has a nice atmosphere going. Magnetic field overlap by the stronger ones. You can get a small magnet in your hand and it rotates to your will when you let it go to overlap the Earth's magnetic poles. Yeah. So yeah, I'm gonna say no to a planet with more than two magnetic poles, but I'm very happy to be proven wrong about that. These days, with the rapidly scrolling comments, makes me feel anxious now just thinking about it. Yeah, the Periscope days with all the comments flicking up so quickly, it was so difficult to keep up. It was a bit overwhelming, but it did teach me good multitasking. Like I reached the point with Periscope where I could write down questions while answering other questions. And when I reached that point, I was like, haha, I figured out how to do these things properly. You know, I love that we have so many questions today. This is super fun. I love answering all of these questions. So please don't feel like you can't ask questions. Keep them coming. And it's my job to keep up, and it's always fun. It's always fun to try to keep up. Comment from Paul, 18 people watching right now. Please click thumbs up. Yes, if you haven't done so already, like the video, leave a comment, subscribe, click all of the usual YouTube things. It really does help. It does boost engagement, and I really do appreciate when everyone does that. Okay. Productivity and clicking the thumbs up button is important. Yes, please do be productive today by clicking the thumbs up button on YouTube, on the video. If you're watching on Twitch, there's also buttons you can click that make stuff happen. I have not yet figured out Twitch completely, so just press buttons and see what happens. Please don't press the thumbs down button, press thumbs up button. I do like those. Where is there radioactive matter in the universe? In bananas. Bananas are radioactive, but like in very small amounts, so don't worry about it. There's a lot of radioactive matter in the universe now, because radioactive is basically anything that decays, and if you wait long enough, most things do decay. Now, if you're talking about radioactive, like the ones that we use here for nuclear reactors and stuff, now that is a bit harder to achieve in the universe because you need these like heavier elements that then have this level of radioactivity. But then you can go to things like supernova or places where you can have enough energy and density to form these heavier elements. Okay, I see some comments here about mind-blowing question. I can't remember what question that was referring to. Let's see. Multiple circulating metallic cores, would that produce multiple poles? Maybe. I'm not sure. Can a planet have multiple magnetic poles? I'm writing this down because I think it's a very interesting question, and I'm again not able to think of a way where you would have that, because David's comment here, David Howden, multiple circulating metallic cores. How would you have multiple cores circulating, like rotating in different ways? I think what would actually happen is so let's imagine that you have two different magnetic cores rotating in different ways. I think the resulting magnetic field would be a superposition of both, not two distinct magnetic fields. I think they would kind of overlap. So I don't think you'd be able to get distinct poles and distinct magnetic fields. I think they would overlap. But again, I'm not completely sure on this. And I do think that means I am almost completely caught up with the questions. Last one from James here, or last one that I'm reading here. Is there any subject in your field that you wouldn't mind investigating other than the one you are in? What about science? What about what science field you would be in if it couldn't be cosmology? I love these questions. So if I wasn't studying cosmology, let's go back here, because the question just disappeared. If I wasn't studying cosmology, I think something that I would be really interested in is biophysics. So the physics of how biological systems work. because I took a course on like introduction to biophysics at some point, and it covered things like how proteins fold to be in specific shapes, which is fascinating. There's like proteins are basically made up of like 20 building blocks, but then they can fold in different ways, and you get these 3D geometrical shapes. And based on this, literally all life on Earth is possible. And there's like billions of different possible ways you can fold these proteins. Some are viable, some are not. And the physics behind it is absolutely fascinating. Another thing that we covered in biophysics is like how different organisms move or how different things move. And like the way different products move throughout your body is vastly different. Like some things can be absorbed by your skin, some can't, some can be absorbed by different parts of your system. You know, there are these like protein carriers that almost look like they've got legs and that they're moving, and it's literally just an inanimate chunk of matter in your body, and it has a special way of moving. And you know, you have slugs or snakes that have this whole like slithering motion, and all of this is grounded in physics. And I think it's really, really cool. So I would definitely was very tempted to go into biophysics at some point. So I feel like I easily could have ended up in biophysics, if not cosmology. Then the question of, is there any subject in your field that you wouldn't mind investigating other than the one you're working on? So more narrowed down to cosmology. Obviously, CMB, dark matter, gravitational waves. I've moved topic a lot. These are all ones I've really enjoyed working on. I think black holes are something I've never worked on myself directly, but it's something I would really enjoy working on. And I just feel like there's so many things in cosmology that I would enjoy working on. And the nice thing is I happen to work on multiple different topics. If you look through my publication list at some point, there's like 20 different topics and then like 23 papers, 20 different topics, because there's so much in cosmology that I find fun. But yeah, I think another field of physics that I would definitely have loved to gone into that wouldn't be cosmology would be biophysics. And then if you want to say like, what would I study that is science that is not physics in any way, then I think it would be neuroscience, because neuroscience is just super fascinating. But yes, that is a very, very cool question. Okay, this is a space, or just based on that name, I'm guessing you're going to ask something technical. And the question is indeed, can you quickly answer a technical question? Potentially. I was struggling to giving one-tailed priors for the negative cosmological constant in MC. Okay, that is a super technical question. And yeah, I feel like I don't have enough information from your side to answer that. So that feels like a very specialized question. If it's something that I have worked on, feel free to email me about it and I can potentially answer it there. But right now, nothing comes to mind as to how I would do that in MC. I feel like it very much depends on the type of cosmological constant and how you're dealing with it and what you're doing with it in MC. So I feel like I don't have enough information to answer that question, unfortunately. You study psychology, physics led you here, and you ended up in black holes. Great. Yeah, I mean, black holes is a really fun topic. So I'm glad you're enjoying black holes, and I'm glad you're here. Comment from John Redford, going back to Lyman alpha. For Lyman alpha, I was wondering, since the spacing of the lines is determined by the rate redshift, if there would be a superimposed signal from expansion on the smaller signal of the gas clouds. Interesting. See, I don't think we factor in the expansion of space-time when we're doing Lyman alpha, or like we obviously factor in the expansion of space-time with the scale factor, but I'm not sure if we factor in dark energy to that level, because I don't think it would play a role. But that is a very interesting question. You know, when we do Lyman alpha, first we're looking at things that are like redshift 4 or 5 or 6 even. And I feel like that is so close that in order for that to actually have like this effect of the changing redshift, I'm not sure if it would play a role in Lyman alpha. I have in mind that Lyman alpha is again too small to think about this big this big effect of the changing of the expansion of the universe. But it is a very cool topic, and I have made a note of it to look into that. So it is a cool topic, and thank you for bringing that up. Okay, I see a question from Pirate. Last question I'm going to answer, because we are at 1 hour 5 minutes. I did not even attempt to cut this stream off early. Like I said, I was going to do at some point. You all knew I wasn't going to cut it off early. I never do. I say something like, yeah, we won't go for 1 hour today, and then, you know what, we always do. Okay. My voice is very much going now. I'm out of tea, so last question. Question from Pirate. If atoms are removed from standard science, what kind of science it would be in particles? I mean, if you get rid of atoms, if you get rid of normal matter, you're left with the 95% of the universe that is dark matter and dark energy, which is still very, very fun. You know, you are removing the smallest contribution to the energy. As to what, you know, what would science look like? What would everything look like? It's such a hypothetical question. Like, if you remove atoms, you remove us. So then what type of science would happen? Would there even be science if there's no atoms, for there to be no people? Can you still have science that is like very much a human-made concept? Of course, I'm sure other species would have their own type of science as well. So this is an interesting question. I'm not completely sure how to answer that, but I do like the question. Whew. Okay, I think I think I got through all of the questions today. So many fun questions, so many varied topics. I feel like you all had such cool questions today, and such different topics. It was really, really fun, and I do think we covered everything. So thank you everyone for your questions. This has been really fun, as always. It's always so fun to come in here. You know, I come in without any idea about what you're going to ask, and you always seem to ask me super fun questions. I'm still thinking about how best to explain how light moves through things and massive objects move slower or faster sometimes. I've put notes down to look up about magnetic poles in planets and about Sachs-Wolf effects with Lyman alpha. So I feel like you've all given me homework today, and that is very, very fun. Doesn't necessarily mean I'm actually going to look this up, because what's going to happen now is I'm going to put this piece of paper away and take it out again next Sunday before the stream and be like, oh, I was supposed to look these things up. But yes, thank you, everyone. This has been really fun. I love all of your questions. If you haven't done so yet, subscribe, leave a comment, like the video, all of the usual stuff. And I'm just going to mention something that's just mentioning it here. Not official yet, nothing that I'm allowed to talk about publicly. I'm starting another science outreach project. You're going to see updates soon. Stay tuned. I'm not going to tell you what it is. I'm not going to tell you anything about it, but there is something else coming. There's going to be something in addition to, not instead of, there's going to be in addition to Cup of Cosmology. I'm planning something else. It's in very much the early stages, but just stay tuned. Stay tuned. I'm going to start hyping it up gradually. Just keep an eye out for something. Something is coming. How very, very mysterious. Okay. Before my voice goes completely, time to wrap up the stream. Cup of Cosmology should be back online next Sunday, same time as always. That is 7 p.m. if you're in Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. In principle, Cup of Cosmology should be back online next Sunday. I hope you'll bring as many fun questions as you did today. I hope you bring as much enthusiasm as you did today, because this has been super fun. So I hope to see you all again next Sunday, same time as always. And I hope in the meantime, you'll stay safe and take care of each other.